Okay, so I'm going to talk now about erosion measurement. So we can actually measure the amount of sediment in water. We can measure how the surface changes. We can do plot studies. We can use our rainfall simulator and flumes. We can use gauging stations in rivers. We can use chemical methods like isotopes. And we can use a whole bunch of different point-based measurements. So I'm going to talk about some of those. So we can measure erosion in the field or in the laboratory, and sometimes there's no getting over doing field measurements because they're often the most reliable estimates of long-term erosion rates. But they are difficult to conduct, challenging to interpret some of the results, and also challenging to obtain some of those results, right? It's a lot of intensive effort and lots of experience required to do that properly. Laboratory testing allows you to use what-if scenarios, right? So if you're developing something new for the first time and you want to do some design, you could build it in the field, but that's going to be really expensive, right? So you could build 20 different slopes with different angles in the field, but you know the cost of building hundreds of hill slopes at a mine site is just infeasible. So laboratory testing is sometimes the best way to do a what-if type scenario. To come up with a good design. There's also modelling, and we'll come to that down the track. Right, so sediments and landscapes. Now I'm going to talk in a lecture or two about actually how landscapes erode, or the characteristics of a landscape that you can interpret, but for now we're just going to concentrate on actually how you measure erosion rates in a landscape. Now, erosion rates in a landscape are going to be very, very slow. Right? Real landscapes erode very slowly. So you've got to be careful about how you go about estimating those erosion rates. Right? If you get it wrong by just a few percent, it's going to make a long difference in a few thousand years. If you're interested in, say, managing what's happening at Ranger uranium mine, where it can be important to understand what's happening in 10,000 years. For example. So sediment transport rates are often expressed in terms of tonnes per hectare per year, right? A mass per unit area per unit time, or in terms of an average elevation drop, right? So the change in height per year or per 1,000 years, for example. And we can do these using direct measurements, right? So observation. They provide us with sort of qualitative descriptions. We can look at a site and say, oh, I see a rill, or I see a gully, or I see a soil pedestal where the rock's sitting on top of it, or I can see exposed roots in a tree. So in the lifetime of that tree, there must have been some erosion going on. Right? Or you can actually do measurements of how gullies and rills and soil pedestals are changing with time. Or how they may have changed, using some accurate estimates of how they might have changed by using surveying techniques, right? And these direct measurements provide us with reasonable estimates of denudation, right? The change in elevation with time. So here's what I mean. Here's a gully that has moved off into the distance there with a colleague standing in the distance. You can see the vertical walls of the gully. And we know how old this landscape is because it's a post-mining landscape, right? So we can get an estimate of this volume change over a certain period of time. Here's an example of a soil pedestal. So we can estimate the denudation rate here because this is a rock fragment that was sitting on the soil surface that has resisted raindrop impact. It's also resisted some overland flow. And we have a change in elevation here of obviously a few centimetres over some period of time that we can estimate by other means. The keys are there for scale. So, for example, you can go to a field site, you can map out a gully, you can map its width, its height, you can even map some of the shape of the gully, right? Its cross-sectional areas. And then you can estimate how much total volume of sediment was lost. So, like I said before, you can measure the depth of gullying, the gully volume. You can estimate if you, for example, have a number of gullies in a different area, you can estimate the average soil loss across an area, but you need to know the age of the site. And you actually may never really know the height of the initial surface. So even though you have, soil pedestals and things like that, it may have started to decrease before you started to get, pedestals being developed. Right, so you could potentially underestimate your erosion rates. Right, so that was direct measurement. Now we can have other direct measurements, but using a little bit more sophisticated. So we can use photogrammetry. So here's a really bad picture from Germany, apologies, of an airplane flying through the sky, taking photos of the surface, from which you can develop three-dimensional pictures. Now we can do this using drones now, right? And Nick Callow does this with his photogrammetry methods from his drone camera, and you can map out reasonably large areas in a short amount of time with accuracies, say from the drone, of just a few millimeters, right? So if you've got erosion that's more than that, you can map it out using photogrammetric methods. Here's an example. There's something that is similar to Nick's octocopter with a camera on here, and now there's photogrammetric methods where you just snap a whole heap of photos. It stitches all those photos together, and using a bit of actually quite simple mathematics, it reconstructs surface topography. So you can map out gullies and rills, or you can refly landscapes over different periods of time to map out how the surface is changing in 3 dimensions over time. You can use terrestrial laser scanners. So here's exactly one of those. It shoots off a laser off into the distance. Maybe you might have a reference panel off in the distance, and then it sort of measures how long it takes for the laser to hit various points and reflect back, and you can get reasonably accurate measures of the soil surface. Now it can't shoot through canopies, so you may have to deal with a whole heap of image processing to get accurate measures of changes in the soil surface, for example, if the laser's hitting the canopy. But you can do it, and laser scanners are being used more and more. So you can use plot studies at field sites, right? So you can set up a permanent research station at a site and one advantage of that is you can actually bound off an area so that you know the area over which something's happening, and you can know the slope, and you can know the length of potentially length of overland flow, and you can characterize the soil type, and then you can measure runoff and you can measure soil loss, right? And you can set up standardized plots as well, right? So a typical standardized plot might be 22 meters long by 8 meters wide. You have sheet metal on the sides, which extends up, or plastic, which extends 150 to 200 millimeters into the ground and a little bit above. And then at the bottom, you can collect the runoff and erosion in gutters and put it into barrels, right, and measure it. So that's what a standardized plot could look like, for example. And these are other types of observation plots. These are in natural sites, I think up in the Northern Territory. So we have some catchments up here, which are bounded. And at the bottom here, here's a small little subcatchment, and here's another little subcatchment. And they've got some guttering on the sides to make sure that we sort of know the area over which the flow's happening. And at the bottom here, we've got some runoff troughs, flumes, which are measuring the flow rate. And we can also sample the erosion, or sample the sediments that are coming out, either by subsampling the water or having the flow go into some sort of collector, which collects the sediment. This is what some data could look like from that, for example. So we have some rainfall events of certain depths, so 42 mils, 30 mils, 16 mils. We have a certain amount of runoff being generated. That should have units, but it doesn't. We should have, we can measure the suspended load, right? This is the sediment that is actually in the full flow. And this is the bed load. So this is the sediment and the rocks and all that sort of stuff that are moved along the bottom, but not actually transported up into the flow. You can measure also the inter-rill erosion, right? And similarly like that at different plots. Here's another example from partly 2005. These flat, shrubby, bushlands up in, I think, in northern Queensland. They have these long partial flumes, which are good for measuring sediments and erosion. You have some sort of sampler over here, which is sampling the suspended load in the flow. And these sorts of flumes here are good for allowing sediments to move through and not clog up the flume. There's a data logger off to the side, which you can see it's moving across the top of the flume here. So it's actually got a little detector which beams a bit of light down to the base of the flume or the top of the water and measures either acoustic or light. It's measuring the height of water, and so you can estimate the flow rate from the height through the flume. So from that Bartley experiment, the 3 different catchments, natural, vegetated and non-vegetated, you can see here they're measuring sediment concentrations in the suspended load as a function of these are different catchments, and these are different plots within those catchments. You can see that non-vegetated plots, generally speaking, have much higher erosion rates than the vegetated and the natural ones. Right? The vegetated ones, they've got some pasture grazing going on. The natural sites all have the lowest erosion rates and are similar amongst the different catchments. Okay, so that's something that you can do with the results that you measure. You can measure erosion in the lab or the field using rainfall simulators or flumes, for example. So the nice bit about these types of measurements is that you can control things like the rainfall, and you can also make up your own soil types if you've got their facilities to do that. You can monitor how the system is evolving over short periods of time, and you can do really detailed observations. Right? Some of the disadvantages for using, say, rainfall simulations, flumes like that, are that the initial and boundary conditions that you apply in the experiment may be very different to what's going on a natural hill. Right? You may have very short length of plots, so you may be measuring erosion processes that are not necessarily occurring in the field. So you have to design and interpret your experiments carefully. The materials that you use may be different because you might have disturbed the soil and then tried to place it back into some flume that you do your experiment on, but of course that's disturbed all the soil properties and you've mixed things up a bit. You've moved rock around, so it might not reflect actually how the soil is in a real site. The effects of scale I mentioned before, right? So it might take a certain amount of time for the flow velocity to get high enough to generate erosion, and the erosion process might only be occurring at certain places in a real site as compared to your experiment. And these experiments can be time consuming. So look, here's a rainfall simulator that's almost identical to the one that we had. It's a little bit longer. They've set up a bounds on the edge of this little plot so they know the area. They've got rain gauges in there. They've got their collector at the bottom here with some tubing coming off so they can measure the runoff from the erosion. There's their reservoir with the water going up the pump and so on. So they can control, do a whole bunch of experiments on these sites, looking at the effect of slope and rock armour and all sorts of things, right? Here's another experiment. We're using the same device in a natural site. And again, similar sort of thing, looking at how some engineered road is potentially leading to sediment delivery into a nearby stream. Okay. There's an example of a flume. For example, instead of applying rainfall at the top, you apply flow velocity at one end, and then you can erode this. You can erode this landscape. For example, you might want to design a runoff channel, and if you mix up rock with some initial sediment, you want to estimate whether you have enough rock in there to prevent your channel from eroding before it can do its job, right? Diverting rainfall. You can look at things like slope and plot length and play with that and come up with a good design. Now you can also measure things like the sediment and stream sediment concentration, both as bed load or suspended load in rivers. And here is, it's not very informative, but trust me, there's a logger which is sampling water quality. There's a water quality sampler here. But within this device here, you can sample the suspended load and estimate the erosion, estimate how much erosion is happening across your entire catchment. There's rain gauges, although why it's situated underneath a bunch of trees, I don't know. And you can also measure the bed load, right? So they have bed load detectors which measure how much material is moving across the bottom of the creek. So here's an example of what that data might look like. So total suspended load concentration, right, grams in a litre of the river water as a function of time. And you can see it's very peaky, right? So you get high resolution data spanning long periods of time, and you can relate things like land use and climate variability and all that sort of stuff to erosion rates. You can relate sediment load to discharge, right? And we often use relationships like this in our models. So if we have a hydrological model that's measuring, predicting how much water comes down the catchment, we can use an equation like this to predict how quickly our landscape, our catchment is eroding. There's chemical methods, cesium methods for estimating erosion, right? So we had the bombs that went up with all the nuclear testing in the 1950s and peaking in the 1960s, and has been decreasing ever since. And that fallout from cesium fallout from those experiments is still with us today, and it's sitting in the soil. And we can actually go back and measure cesium concentrations in the soil to work out how much soil is being deposited above that material in the time since that bomb peak, right, in the 1960s, to get an estimate for erosion rates. So, for example, we have a reference site at the top of the hill, and you can measure the cesium concentration as a function of soil depth. And then as you move, say, off the top of the hill down the slope, you get very different cesium profiles in the soil, and that can tell you about what's happening. In this case, we have a plough layer which has mixed up that cesium in that soil surface. So we've got mixing and potentially movement of particles, with time. And so we get a uniform distribution of cesium with depth down to this point, and then a decrease beyond that. But in this part of the hill, we have an eroding slope, right? And so it's still cultivated, but we have a decrease in concentration down at the plough depth, which is suggesting that we've got a loss of material. And then at the bottom of the hill, we have an increased cesium concentrations and then a decrease again, which is suggesting that we have deposition of soils down the bottom of the hill, right? And you can measure average concentrations over a certain depth, for example, and that's what this does. A reference site, and you can see changes in the millibecquerels of radiation that's measured in the soil as a function of location, right? There's other methods which I'm not going to go into. You can look up the papers if you're interested, but there's optically stimulated luminescence, and essentially that's based on quartz grains in the soils. So interestingly, when a quartz grain is impacted by radiation from the sun, by sunlight, it resets this luminescence clock in the chemicals in the crystals in the quartz, which once it's buried, the clock ticks away, and you can measure, if you dig up that soil without exposing it to light again, you can measure that clock in the soil, and it tells you how long that bit of soil has been buried, right? That can tell you something about erosion rates. There's also isotopes of beryllium, aluminium, and other cosmogenic nuclides, estimating denudation rates or soil production rates in soil. And there's a really good paper I recommend you read if you get a chance by Heimsath, which describes the use of this techniques in estimating soil production rates in soil and hill slopes. And then there's point measurements that I've seen some of you try in the lab using erosion pins, splash funnels or splash caps, for example. So, for example, we could push an erosion pin into the soil, and then if it's been eroding, we can measure the change in height of that erosion pin over time. If it's depositing, then we can measure the height of soil above the pin, or as the height of soil as it's moved up a pin, for example. And we can also use these pins to measure the direction of sediment flux, and I'll come to that in a sec. But if you're just using individual pins, for example, you've got pins pushed in and you can measure the changes in erosion or changes in height of those pins over time, and that tells you how much the surface has eroded at different points along a landscape. Now, I think in your experiments it's going to be quite difficult given the time frames involved and the type of materials we're using. But you can see that if you leave your pins in place for several years at a place, that potentially can measure millimeters rates of change using a very simple technique. And this is sort of what I mean, right? So you've got 3 pins in the soil. Where's our initial surface, the dashed line, and then our new surface. And at this pin here, the height, this height here was initially here, and then it's increased by dz1 at that point. And it's only the height of that pin above the soil surface is only increased by a little bit here. And in this point here, it's actually decreased, which means there's been some deposition. So measuring those changes in heights can tell us about where erosion is taking place. I'm going to skip this, but you can read this if you're interested. And we often describe an elevation balance by the... What? I better get that. Sorry about that, that was me nearly setting fire to my house. Right, Okay, so the extra, and that's divided by the porosity of the material, right? Or 1 minus the porosity of the material. So remember the landscape is made up of soil, and that porosity occupies some volume. So we've got to account for that volume. We've got to account for that volume when we do the elevation balance, right? And this upside down triangle here is actually called the divergence, right? And essentially it just means this. If you have a look down the bottom, it just means the change in sediment flux with position. The difference between the sediment flux coming in to that point and the sediment flux leaving that point, right? And that's that delta QS divided by delta X, and delta X is some representative distance. Okay? I'm going to skip all that because you guys are probably not interested. We can also think about it in 2 dimensions, right? But we'll get to that in a sec. So we can think about the change in this area as being related to that sediment flux, right? Because if we divide this area by this distance, it's essentially similar to our delta QS divided by delta X, right? So this change in area divided by that distance is also our sediment flux. And you can see that makes sense, right? Because that's how much our elevation has changed over that distance. So we can use erosion pins in 2 dimensions as well, and we actually do this in the field, and we set up nests of erosion pins like this. So a set of 9, for example. And what that allows us to do is, by measuring the change at each pin, we can estimate a sediment flux in the X direction, and we can estimate a component of the sediment flux in the Y direction. And if we go back to and this divergence here is really an addition of vectors. So this is a vector in the X direction. This is a vector in the Y direction. It's not a scalar addition, it's a vector addition. That gives us a new vector, which is equal to the magnitude of those 2 vectors combined, right? Which is this new vector here, the blue line, which gives us both the magnitude of the sediment flux, but also the direction, right? So it can tell us which direction the sediments are moving to on the average from this point. Right? And so if we do that in different parts of the hill slope, we can get an idea for which are the dominant directions of sediment movement, if it's not immediately obvious. All right, another way is to use little sediment traps, right? So we can set up a little plot like this with plants growing in it, with a boundary, and we have a series of collectors going in. And they often have series of collectors like this because we have sediment being moved, we have some suspended load, and when this fills up, then it goes into this collector, and then it goes into this collector, and so on, right? So we can measure an average rate over a long period of time, collecting all the flow and all the sediment. We can measure things like rain splash. So here's a rain splash collector, and we have 1, 2, 3, 4 collectors on the side of this hill here, and that gives us an estimate of not only the total amount of sediment by adding up all the 4 chambers, but it gives us an estimate of the distance effect. So remember when I said downslope of a splash point, you get more and more sediment collected? Well, what we can measure is the distance effect. So we should get most amount of sediment collected in number 1, a little bit less in sediment 2, even less in sediment 3 in chamber 4, and then finally a small amount in chamber 4. So we can estimate, the downslope component of sediment transport by rain splash using a little collector like this. You can dig a hole in the ground, put a funnel in it and a bottle at the end of it and measure a splash like that. Or you can have a little bit more sophisticated splash cup, for example. Bit of soil and then little chambers collecting the splash in various directions. And here's an experiment that was done using a rainfall simulator using exactly that. And you can measure, for example, the weight of detached grains as a function of distance. And okay, it's not immediately clear, but there's a little bit of a peak and then a decrease, generally speaking, for most of these. And very often it's useful, and we're beginning to do more and more of this, is to use multi-scale assessments, because erosion at different scales is impacted by different processes, right? So at small scales it might be impacted by splash. At intermediate scales it might be impacted by interrill and rill erosion, and then at larger scales finally by gully erosion. So you can set up nested experiments within a hill slope to look at each of these interacting processes. And so this was done at a mine site. This is from Luis Martin from Kings Park, and he set up some multi-scale experiments. Here's a boundary there, there's a gully running through the middle here, here's another one, and here's another one. And within that, they also set up little of those runoff plots, right, that were concentrated around different vegetation types, because that's what they were particularly interested in. They had some rain gauges and also some other sediment collectors and soil moisture probes and various other things, right? And they had these little sediment collectors were called Gerlach plots. And so they were interested in looking at how different vegetation communities or types impacted the erosion in those different areas, right? So multi-scale assessments can be important. So in summary, you can measure erosion at a whole bunch of different scales, from the point to small plots to larger plots to hill slopes, all the way up to catchments, and you can do multi-scale nested experiments measurements to estimate erosion processes that are going on. Okay, monitoring can be important. Experimental methods are important for design, and also there's not just direct measurements of measuring sediment and changes in sediment amount, but also indirect methods like isotopes for measuring sediment transport rates.